and we'll go ahead and get started.
Thanks so much, Megan, and thanks to everyone once again for joining us today in this second installment of our state and transition simulation modeling webinar series. Just as a reminder, we are the Nature Conservancy's Landfire team, and along with the U.S. Geological Survey, we are partners in the Landfire program. The Landfire program is led and primarily funded by the U.S. Forest Service Fire and Aviation Branch and the U.S. Department of the Interior Office of Wildland Fire. So last week, we focused on how Landfire implemented state and transition simulation modeling, just to start this conversation. Because of our personal program goals, our implementation was very wide, but it was shallow. We created 1,000 consistent, relatively simple, non-spatial vegetation dynamics models. But during that process, we barely scratched the surface of the potential for this technology. So today, what we want to do is really throw open the doors for you. Leonardo Friga is going to describe other implementations of state and transition simulation modeling that we hope demonstrates the wide world of opportunities for this platform. We hope to sort of spark your imagination a bit. So I ask you not to focus necessarily on the extreme details of what Leo's going to present today, but to start to imagine the possibilities of this technology for you and your work. So this is about sparking your imagination. So buckle up, everybody. I'm going to turn it over to Leo, and thanks for participating, and hope to talk to everybody when this is all over. Thank you.
Thanks for the introduction, Jim. Can folks hear me okay? Yes.
Sounds
and
great.
do you see the full screen sort of slide presentation? Am I sharing the right screen?
Yep, you
Okay.
look good and
I
you
see
sound good,
Megan
and yeah, we're good.
nodding there. Excellent. Okay, so before I jump into the details of the state and transition simulation modeling applications, I just want to say a few words about ApexRMS. That's the company that develops the STSM software. We are a small group of ecologists and software developers, and our focus is on developing software tools and applying them to ecological forecasting problems. We have a long history of collaborating with the Nature Conservancy Landfire team that for some of us goes as far back as 2002. And that has been a really fruitful collaboration. And I would say that, in a big part, thanks to that collaboration, a lot of what you'll see in the presentation today has been made possible. Amongst the company, I would say that collectively, probably we have over 40 years of experience working with state and transition simulation models. So this is part of the 3-part mini-series, and last week, Corey spoke about state and transition simulation models, specifically the Landfire BPS models, and she gave a bit of an overview of state and transition simulation models. Today, I am going to be talking, as Jim said, about some example applications outside of Landfire, just to give people a sense of the full breadth of, what is the work that other folks are doing using these tools. I'll also give a bit of an overview of the software, which is STSM and SyncroSim, and as well, I will give a bit of a demonstration both using the graphical user interface and the R package for those of you who are interested in learning a little bit about that. And I'll try to keep both the examples and the demonstration fairly high level, so it's suitable for a wide ranging audience. I'm not going to get super technical, but I will also give you information on where you can learn more if you are really interested in getting into the details. Next week, just to mention, there will be another presentation by Randy Swati and Priscilla Niamai, and they're going to be talking about using state and transition simulation models in the classroom. But for today, I'll start out. I know Corey gave already an overview of state and transition simulation models using the landfire example, but for those folks who weren't able to be here last week and a little bit as review, I'm going to again give an overview of what these models are and how they work. I'll talk a little bit about the software that we use, state and transition simulation modeling. And I'm going to focus on 3 example applications, and my choice of these applications again was to give you a sense of the diversity of problems. So state and transition simulation models are really a framework that's very flexible and can be applied to many different ecosystems and natural resource management problems when you're working at the landscape scale. So the 3 examples that I'm going to focus on, one of them is looking at projecting land use, land cover change, and associated changes in ecosystem carbon. And this is an example from the state of Hawaii. I'm going to be talking about an example that looks at the interaction between fire and invasive species in the Southwest. And then I'll wrap up with a Canadian example looking at forecasting cumulative effects of different stressors on the habitat of a particular species. And then I'll talk a little bit about the SyncroSim software and the rsyncrosim package for R. I'll give a demonstration and wrap up just providing a few resources that folks can turn to if they want to learn more. So when we talk about state and transition models, going back to the origin of this kind of modeling approach, we're often talking about conceptual models that describe what can happen to a particular piece of land in terms of the vegetation communities that can be present there, and the changes that would move a particular piece of land from what we call one state to another. So the states really represent different vegetation communities, species composition, vegetation density, those kinds of things. And the transitions represent either natural or management processes that can move the vegetation between these states. This is something that originated in the late 90s for Australian rangelands and has since had a lot of resonance, particularly with rangeland ecologists, because you do see these kind of state transitions in rangeland systems where some events such as the introduction of an exotic species or a severe drought can create a change in a vegetation community that is very discrete and often not so easily reversible. So those are the conceptual models. And over time, I think some ecologists that were looking more at quantitative modeling at landscapes thought that these might be a useful jumping off point for trying to develop some tools to look at forecasting changes on a landscape over time. And so this is where state and transition simulation modeling comes in with the word simulation added. And so these are quantitative models. The origins date back to the early 90s in the Western US, where land management agencies were looking at different policy and management decisions for large landscapes. And at the time, the models available were mainly focused on forests, and something was needed to be able to make forecasts for vegetation communities that extended beyond forest types. So mixed landscapes with mixed vegetation types, including forests, grasslands, wetlands, and so on. And so starting in the 90s, there was a suite of software tools that started to get developed. And many of you will have heard particularly of VDDT, which is what Landfire used for a large part of the development of the state and transition models that they have been working with. And VDDT was developed by a Canadian company called ESSA Technologies, who also developed a spatial tool called TELSA. And those tools were quite useful for a number of years, but over time, there were some challenges identified, both with being able to scale them up to modeling large landscapes and with their usability. And so that eventually led to the development of STSM. First version was released in 2013, and that was developed by ApexRMS, the company that I work with. And there's a paper I'm going to talk a little bit more about that outlines the methodology behind state and transition simulation models. So this really lays out the theoretical framework for the approach and provides an example. And this is one of the examples that I'm going to be talking about today. So at a very high level, I'm going to start out with a very simple model example where we have a landscape that we're interested in creating some kind of forecast over time for. And so the first thing we need to do when we're using state and transition simulation models is come up with some sort of a classification system for this landscape where we can assign every location to a particular vegetation state. And so here I've decided that the classification that I'm going to use for my model breaks the landscape up into what we call 3 state classes. Now, just if you're coming from the rangeland communities, I think there's a very specific meaning to the word of the use state versus phase. When we're talking about the state and transition simulation models, we use the term a little bit more loosely. So when I refer to a state class, really I'm talking about a box that I'm going to classify a particular type of vegetation community that I'm going to classify for a particular location. And the states that you choose to use in your model are going to depend a lot on 2 things. One of them is what information do you have available to you to be able to classify and quantify your landscape? And also, what are the modeling questions that you're asking? So depending on your modeling questions, your model could look quite different. Once I've classified my landscape, I also can track other information about these particular locations. So for this particular example, and one that is commonly used, is the age of a particular location. That might mean, the age since a replacement event or the time since the last transition. So again, depending on the modeling question, the model you're going to build, the age might mean different things. So I've classified my landscape. I've got some more information, in this case, the age of each location. And now the other thing I need to do is I need to create some kind of a conceptual model that describes how a particular location on this landscape might change from one state to another. And that conceptual model includes, my classification, the boxes that I've shown in the previous slide, but it also needs to include the processes that would drive change from one box to another. And in this very simple example, I've got 3 different processes. One of them is the process of vegetation succession, which in this case will transition a deciduous stand to a mixed stand to a conifer stand. And then natural disturbance, in this case fire, which will transition mixed and conifer stands back to deciduous, and could also occur in deciduous stands, but not lead to any transition. So deciduous would remain as deciduous. And then finally, I've got a land management action, in this case timber harvest, which occurs only in the coniferous state, and that transitions to deciduous. So far, my model is purely conceptual. There's no quantification around it. But if I then assign rates to the different transitions and describe how often they occur over time, then I have what I call a state and transition simulation model, and I can take a particular location and run a projection for what might happen to that location over time, both in terms of its state class and in this case as well, its age. And if I scale that up to my whole landscape, then I can take my starting landscape and make some kind of a projection over time for the entire landscape as well. So this is again what we call a state and transition simulation model. And because it's a stochastic model, we usually run the model many times. We call these Monte Carlo realizations. And that gives us a sense both of the kind of expectation of what the landscape might look like at some point in the future, but also a sense of what the variability in that expectation might be. And so that in this little simple example is represented by the error bar shown on the screen. So some of the key features of the approach is that the probability of a transition can vary according to the vegetation state. So in this case, probabilities of fire for mixed and coniferous are shown to be different. The probability can be contingent on other state variables. So in this case, the process of succession is contingent on the age of a particular location. So we have succession occurring in this case with a probability of 1 if the age reaches 10, and from mixed to conifer at the age of 20. And then in addition, one of the things you can do with state and transition simulation models is instead of using probabilities, you can assign things like targets. So you could say, for this landscape, harvest 1,000 hectares per year of conifer, but target stands that are older than 65 years of age. And then the other feature, often you'll hear about state and transition simulation models or have them compared to what we call Markov chain models, which are essentially matrix models of landscape change. And one key difference between them is that those matrix models assign a single probability for transitions between states. In this case, you can have multiple pathways. So for example, you can get from conifer to deciduous either through a fire or through a timber harvest transition. So that's a very simple example. I'll come back to this one a little bit more when I get into the applications. But now just a little bit about the software behind the modeling. So you'll hear two terms used when we're talking about the software. One of them is SyncroSim and the other is STSM. And SyncroSim is a generalized framework for any kind of scenario-based stochastic simulation over time that supports what we call plugin models or packages. And the way SyncroSim came about was actually we're working with state and transition simulation models, and we realized that a lot of the things that modelers do are the same independent of what kind of modeling you're doing. So you need to track all of your modeling inputs and all of your modeling outputs. You need to be able to track model scenarios. You need to be able to visualize both temporal and spatial output. And so we felt like we could take some of those key features and develop them into a software framework that then different kinds of models could be plugged into. And STSim is just one of the packages that plugs into SyncroSim for state and transition simulation models. And it is by far the most popular of the packages. It's been picked up by many researchers around the world. And there's over now, since the release in 2013, there's now over 40 peer-reviewed publications that have used STSim. Okay, so now I'm going to get into a few of the examples applications. So the first is looking at modeling land use and land cover change and ecosystem carbon in the state of Hawaii. And the publications behind this example, there's two of them in Methods in Ecology and Evolution. The first I already mentioned, which is kind of what we call, I guess, the showcase of state and transition simulation modeling that outlines the methodology behind the approach. And then the second one takes into account not just, so far I've just talked about discrete variables like state and age, but takes into account adding continuous variables to your state and transition simulation models, specifically to be able to model carbon. So so far we've talked about in this very simple example model that I showed you discrete variables, and those variables are the state class that occurs in a particular location in space, and the age of that location. So the question is, how do we track continuous variables, and what are the kinds of continuous variables that we may want to track in a state and transition simulation model? And so one of the examples of that is ecosystem carbon, where in any one particular location, you might have different amounts of ecosystem carbons in what we call pools, such as live biomass, dead wood, and in the soil carbon. And there are already modeling tools that you can use for doing this kind of modeling. Some of you may have heard of tools like VenSim and Stella. And the one challenge with these tools is that they're typically non-spatial, and they're they're more deterministic type models, and they're not linked to a landscape. So we thought that linking continuous variables to state and transition simulation modeling could be quite useful if you want to look at landscapes. And so how do we add continuous variables? So here again is the very simple example that I showed you. In this case, just showing the natural succession transitions. And what we first do is we add to the model what we call stocks. So these would correspond in the case of modeling carbon to your different carbon pools. And here, and the stocks that you add can be quite flexible. So nothing is hard coded about what states or what stocks you're adding to your model. But in this simple example, I've got 4 stocks. I've got carbon, can be either in the atmosphere, it can be in living biomass, it can be in dead wood, or it can be in soil organic matter. And once we have the stocks, we add what we call flows, often referred to in carbon modeling as fluxes. So one flow is growth of living biomass that's taking carbon out of the atmosphere and into the living biomass pool. Living biomass undergoes mortality, and so some of that carbon goes to dead wood. And there can be some decomposition of that dead wood that puts some of that living biomass into the soil. So this so far is a state and transition simulation model with stocks and flows. And the key thing about it is when we put this into the state and transition simulation model framework is that it becomes spatially explicit and stochastic. And in particular, now the fluxes, so for example, a fire flux is linked to what's happening with a particular location in the landscape in terms of a transition event and to the state. So the flux rates can also vary between vegetation states. So for example, you could have different growth rates for your deciduous versus your coniferous state classes. And you can see how carbon stocks and fluxes are changing over time for your landscape. So I'll jump now into the example for the state of Hawaii. And this is again from that publication in Methods in Ecology and Evolution, where we have at the top our simple state and transition simulation model, where we have 7 potential states, those being agricultural use on the landscape, grassland, shrubland, develop, forests, and then a special type of forest called plantations that have kind of a rotational type of forest harvest in Hawaii, and then barren lands. These are mainly kind of the high elevation sort of volcanic areas. And on the right, here we see the starting conditions for the year 2011 for our model and how the landscape is classified across all of the state of Hawaii. I've got a box around the Big Island because a lot of the results that I'm going to show in the next few slides are just going to focus so you can see a little bit more of the detail on the Big Island. The other thing we do with this landscape is we've also stratified it according to moisture zones. So we've got dry zones, we've got mesic and wet zones. And so one of the things you can do when you stratify a landscape like this is that you can change the probabilities for the transitions depending on what stratum particular location. So in this case, maybe the probability of fire might be highest in the dry zone over the wet zone, for example. Now, underneath all of this, we've got our stock flow model, or what we call our transition flow path, or flow pathways, where we've got the stocks being the atmosphere, living biomass, litter and dead wood, and soil organic matter. And we've got the arrows down here representing the different fluxes that move carbon from one of these stocks to another. And so for this study, one of the things that we did was we needed to initialize the amount of carbon on the landscape. And often this is shown down here. Often it's very difficult to get information on your starting conditions. So one of the approaches is to run over a long time period a spin-up simulation using kind of the historical disturbance regime to try to get at your starting conditions. And there's uncertainty around this. So we do this many times. In the case of this study, we ran the spin-up procedure for 500 years and 100 Monte Carlo realizations. And then when we make our projections, we also make projections for 100 Monte Carlo realizations starting with different starting conditions each time from that spin up. So here's what some of the results for this model look like. So first of all, just looking at land use, land cover change and transitions. On the left, we've got over time from 2011 to 2061, the projected change in different land cover classes. And this is expressed as a proportion of the landscape. So we see over time, the majority of the landscape is in forest, and forest is declining slightly towards the end of the simulation time period. Another big change that we're seeing is increases in the amount of developed state class and decreases in the amount of agriculture as well as grassland, and increases in the amount of shrubland. This is mainly due by that shrub encroachment transition. And because the model is spatially explicit, the other thing we can do is we can show, what is the probability of transitioning over the course of the simulation for any one location. And so that's what's expressed in these maps here of the Big Island. We've got the probability of agricultural contraction being highest here in the northeast corner of the island, but also some possibility for agricultural expansion. So that's areas that are not currently agricultural lands, all becoming agricultural lands. We have probability of wildfire transitions being highest in this particular area and also in the northwest part of the island. Probabilities of shrub encroachment here being highest in a similar area. And then urbanization, you can see the highest probabilities for urbanization are closest to existing urban centers and areas that have some development already. We can also look at, changes, the probability of change in a particular LULC class. So again, this at the top here, we have the LULC classes for a single Monte Carlo realization. And you can see over the 50-year time period, the urban areas here have grown as well. They have grown here. And we can see a transition, a large transition in this area to more agricultural land, so agricultural expansion. And these maps down here show the probability of being in a particular state at the end of the simulation. So in 2061, the areas where there's a probability of being in grassland, shrubland, forest, and developed. And we did the same thing for the moisture zone. So the stratification, the moisture zones were changing over time as well. And so we can see over time, in particular in these boundary zones, where there's some reduction in the amount of area in the wet moisture zone, in particular, an increase in the amount of area in the mesic moisture zone. And here you can see in 2061 the probability of being in one of those moisture zones as being expressed here on the maps. And last slide for this particular case study. So here now, not just talking about land use, land cover change, but talking about ecosystem carbon. On the left, we've got 3 panels over the 50-year time period. The first is looking at net biome production. So if you're above 0, you're a net carbon sink. And if you're below 0, you're a net carbon source. And we've got 2 scenarios shown. So in red is kind of the baseline scenario with only fire transitions. And the blue includes the land use, land cover transitions, including the plantation harvest. So what you see is that generally without the land use, land cover transitions, the landscape is on average fairly neutral. Some years it's going to be carbon source, some years it's going to be a sink. But adding the land use transitions, so things like urbanization and plantation harvest, pushes the landscape into being more of a carbon source than rather a sink. And that's why the blue line, the net biome production, is negative. We see an increase in the atmosphere carbon stock. And then we see also an increase in the amount of biomass being taken out and put into forest products. And again, this is expressed on the maps. So on the left, we've got the projected change in both living biomass and soil organic carbon expressed in kilograms per meter square. And so the warm colors represent areas that are carbon sink, that have had an increase in living biomass and soil organic matter, and the blue areas are carbon source that have had a net decrease. And because, again, it's a stochastic model, there's some uncertainty about the magnitude of those changes, and that's expressed in the two panels on the right. So that's the first example. The next example that I want to show is an example from the Southwest, looking at modeling Buffelgrass invasion, its interaction with fire, and eventually the management actions in terms of trying to reduce both the risk of invasion and the risk of fire. And this is a project that's, oh, and by the way, I should mention the previous example is work that was led by Colin Daniel, and we collaborated on with also Ben Sleater at USGS and Marie-Josée Fortin at the University of Toronto. And then this example is work that's being led by Catherine Jarnovich at USGS. And there's two publications that talk about this work. There's another one in review. One of them is in Ecosphere from 2019. And then the other one is in Scientific Reports from last year. So this is work that's really looked at how do we model a process that we have not historically seen in a particular ecosystem. So in the previous example, a lot of the transition rates we could derive from historical information about what's been happening over time on the island of Hawaii. Now, in this case, we're looking at Buffelgrass invasion and fire in the Southwest. And as you can see in this picture from the Catalina Mountains north of Tucson, in this type of ecosystem, there's a lot of bare ground, and typically it's an ecosystem where you don't see fire. But the introduction of Buffelgrass, as you can see here, all of a sudden creates a continuous fuel bed, and fire becomes something that you need to worry about. But we don't have historical information on fire rates for these areas because Buffelgrass has only been present for the last couple of decades. And until now, the amounts tended to be smaller, but they're starting to become significant on the landscape. And so this is a project that really has involved many different components. In particular, it involved a component of working with experts to develop the model parameters. And so these are folks that are actively managing Buffelgrass on the ground and seeing the rates at which it's expanding and seeing the effectiveness of the treatment actions. Then we needed to work with different kinds of data and other models. So for example, we integrated a habitat suitability model to help us understand where Buffelgrass is most likely to be invading on this particular landscape. And then finally, because we didn't have historic information on fire, we actually brought in a process-based fire growth model, in this case FARSITE, and linked it dynamically with our STSM simulations. So as we're modeling the invasion of Buffelgrass on the landscape, we're pausing STSM and bringing in FARSITE to determine, where and how much fire might be occurring given a certain rate of ignitions happening on the landscape. So the state and transition model for this particular project looks like this. And you'll notice there's some interesting features about it. So first of all, as we move from left to right, we're talking about the amount of Buffelgrass that is present on a particular location. So we've got sites that have no Buffelgrass at all. And then gradually we see only a seed bank, and then percent cover breakpoints. And those percent cover breakpoints were determined through the expert workshops, both in terms of what are the thresholds for being able to effectively manage Buffelgrass, and also as well in terms of the impact on the likelihood that you would have enough fuel to be able to carry a fire across the landscape. The other distinction is kind of on this vertical axis. So you can't, often there'll be invasives on the landscape, but you can't go and do anything about it until you have found them. And so you need to dedicate resources towards inventory and detecting the areas that have been invaded Sometimes you can use remotely sensed approaches, but often you have to get out there on the ground and look for these invasives, and especially if you want to catch them early enough where it's easier to have an impact in terms of management. So we actively wanted to model the inventory process. And so we distinguish between sites where Buffelgrass has yet to be detected, but is present, and sites where Buffelgrass has been detected. And so the yellow arrows represent the transitions where you are actively going and looking at these locations and sometimes effectively detecting them and sometimes not detecting them. Once the Buffelgrass is detected, then the arrows, the orange arrows represent treatment actions. And again, sometimes treatment is effective at reducing the density of Buffelgrass in a particular location. And sometimes it's not, and you remain at the same density. And in fact, once you get to a particular density, over 50% cover, it really requires a repeated effort to be able to get the density down, because there's just so much seed present that just going and treating once is not enough. So you actually go and need to treat 3 years in a row to be able to get below the 50% density of Buffelgrass. And finally, the blue arrows represent that growth of Buffelgrass over time. And then the red arrows represent the conversion. So if you have high densities of Buffelgrass and you have a fire occurring, then that can really lead to a conversion to a Buffelgrass savanna, no longer desert. And that's almost really practically an irreversible state where it's very difficult to get out of that. And it's just treated as a converted landscape. And then the other thing I should say is that this model also incorporates the spread of Buffelgrass from one location to another. So the probability that you will have a transition from uninvaded to a seed bank state really is contingent on, what's happening to your neighbors. If you have neighbors that have Buffelgrass, it is much more likely that you will also eventually get Buffelgrass than if you don't have any neighboring cells that have Buffelgrass. So similarly to the Hawaii example, here's a map of the study area. In this case, it's Saguaro National Park. It's got the Tucson Mountain District up here to the west of the city of Tucson, and the Rincon Mountain District to the east of the city of Tucson. And then the colors represent our initial classification of the landscape for where Buffelgrass is detected or where we anticipate it is likely to be based on the habitat suitability model. So this is then the starting point for our simulations. And so some of the results of those simulations, on the left, we're showing the amount of area in those different state classes. So the worst is the dark brown. Now that's that converted state. The beige colors going from darker to lighter represent the cover classes greater than 50%, 10 to 50%. And then the blue colors are the lower cover classes in the seed bank state. And we see our starting conditions for the Rincon Mountain District and the Tucson Mountain District on the left in 2014. So you can see the Rincon Mountain District already has quite a bit more Buffelgrass to start with than the Tucson Mountain District. And then in 2044, so 30 years later, the forecasts for two scenarios, one with no fire and one with fire. And of course, it takes fire to lead to that conversion. So that's the one on the right. And it also, you see an increase in the amount of area affected by Buffelgrass in the scenario that has fire. And that's shown a little bit more here, where we're kind of summarizing the amount of area invaded by Buffelgrass for the Tucson Mountain District in blue without fire and some of the uncertainty around that forecast, and in red with fire, again with the uncertainty in the forecast at the end. And then the last panel on the right, the dashed line is the same one. So this is with fire, same as the red dashed line here. But then we add also all the different Monte Carlo realizations of how much area burned over time. So a couple of things about this. So over time, there's always some years where you're going to see no fire across your Monte Carlo realizations. And then the dark line represents kind of the mean area burned across the 20 Monte Carlo realizations. Over time, you can see that there's a projected estimate increase in the mean area burned over time for Saguaro National Park. If the Buffelgrass invasion continues, again, these were scenarios that were run without management actions. And we've got another paper in the works that's going to look at some management scenarios, both in terms of how to allocate resources towards both inventory and management of Buffelgrass in the area. So last case study, and I realize I should probably move things along so we can get to the demo. We're okay?
Yeah,
okay.
I mean, we got 17 minutes, but.
Okay,
yeah,
I'll try to wrap up in the next 5 minutes just to make, or next 5-10 minutes, so we have about 5 minutes left of questions towards the end.
Sounds great.
So this last example is an example from Canada where we worked with Andrea Norris and other scientists at Environment and Climate Change Canada to look at forecasting cumulative effects of different stressors on the breeding habitat of an insectivorous songbird. So this is the olive-sided flycatcher. It's a songbird that's present throughout Canada. And since 1970 has seen some pretty large population declines, about 70% decline in the population or in the breeding population of olive-sided flycatcher in Canada. About 40% of the breeding pairs are in British Columbia. So this is where the study focused, and in particular, in the northeast of British Columbia. So this is down here, you've got British Columbia as a whole, and then this is the area in northeastern British Columbia. It's an area near Dawson Creek, just east, here's the Rocky Mountains, so just east of the Rocky Mountains. And so Environment Canada has been either doing or using publicly available point count survey data to try to understand the habitat preferences of olive-sided flycatcher. And so here we can see that they like small forest clearings. So this is areas where there's been cut blocks, and they tend to prefer areas where there's smaller cut blocks, and with where the time since cutting has been sort of intermediate. So they don't like areas that have been very recently cut, and they don't like areas that have been cut a long time ago. They also prefer areas that have been affected by mountain pine beetle. Again, there's both the immediate sort of increase in food for them in these areas, but also there's the structural changes that happen to the forest, as well as the insect community that follows the mountain pine beetle events when you have all of that dead wood present on the landscape and the different habitats that are available. So based on those habitat preferences, here's the state transition model that we developed to look at that area. So on the left, we've got the state transition model with three main kinds of transitions. We're looking at land use, land cover change again. And so we had good data on both the current condition for different land use, land cover classes, but also on the rates of land use, land cover change historically for these areas, in particular, increase in urban and industrial development and agricultural expansion for this area. And then the bottom is, the land use land cover class of forest that's broken up into more states, just so we can track some of those habitat preferences. So whether a particular location has been affected by a mountain pine beetle outbreak, or whether it's been disturbed either by fire or timber harvest, and whether it's pine, which can be affected, whether there's enough pine there to be affected by mountain pine beetle, or whether there isn't enough, in which case it's just being affected by fire and timber harvest. And again, for this particular landscape, we've had some very large mountain pine beetle outbreaks in the last couple of decades. And so those are the pink areas. And then the lighter green areas represent either large fire events, such as this one here, or this one here, as well as some cut blocks that you can see sort of scattered throughout the landscape. And you can see in the sort of the darker green colors, there's a slightly lighter version that also shows the cut blocks. And then you see these large agricultural areas and urban and some small towns that are present in this part of the landscape as well. And so we took that model and projected forward for 3 different management scenarios, as well as 2 fire scenarios. So here's the projected sort of occurrence probability for olive-sided flycatcher in 2020. And then for the 3 management scenarios, we've got a business as usual, which means that both fire, timber harvest, and development continue at historic rates. A scenario where we expanded the area protected from timber harvest and development, which we increased that area from just over about 11% of the landscape to 30% of the landscape. And a scenario where we reduce the maximum cut block size. Typically cut block sizes are closer to about 40 or 50 hectares on average, in some cases, to maximum of 10 hectares in size for cut blocks. And then at the top, we've got a baseline fire scenario and a scenario that increased fire by about 50% from historic rates, which is in line with what some of the climate models are projecting for this area. And so you can see, especially when you're looking at this landscape, that reducing the cut block size can have quite a large impact. The greener colors are slightly higher occurrence probability. The dark green colors are the highest occurrence probability. So reducing the cut block sizes could really make quite a big difference for the occurrence probability. And there is some impact as well of increasing the protected areas, but not as strong as reducing the size of cut blocks, because with protected areas, you're really only still covering 30% of the landscape, whereas the forest harvesting is happening over a much larger portion of that landscape. And again, this summarizes those. So the red colors represent the business as usual scenario, projecting the largest decrease in habitat over the simulation time period. The green reduces that somewhat. That's for the protected area scenario. And then the blue represents the scenarios with reduced cut block size. And there's quite a bit more uncertainty on the impact of those, but in general, projecting less of a decline and possibly an increase in habitat. And again, the darker colors represent the scenarios where there was increased fire, the lighter colors with the baseline fire. So increasing fire has a slight also decrease in the amount of projected habitat. So that's the last example. And I'm going to talk a little bit about running STSM. I'm going to talk both about running it from R using the rSyncrosim package, but as well a little bit about running it from the user interface, because I think many of the folks on the call are not familiar as well with the user interface. So before I get into STSM, again, talking about the software is actually SyncroSim, and STSM is a package for SyncroSim. SyncroSim is Monte Carlo simulator for any kind of models, and it does all of your data management for your model scenarios. And we've been working on SyncroSim over the last 10 years, and it's freely available. You can go onto our website and download it for free. And in a large part, thanks to some of the key sponsors, including Nature Conservancy, USGS, and the Forest Service. And so SyncroSim lets you connect models together and manage the data associated with those models. And those models can be written in any language, R, Python, C#. We even have examples of SyncroSim packages that deal with model executables rather than coded models. You can run NetLogo from SyncroSim. You can run CircuitScape from SyncroSim. And it comes with both a user interface and an R package, as well as a command line API. And so the idea is that anything that you can do from the user interface, you can also do from the command line, which allows you to work in Linux. And you can also do from R, which is nice once you get into very large modeling projects where you're running many, many scenarios and large areas, and it sort of can be very repetitive to be setting all of your model inputs using just a graphical user interface rather than a scripting environment. So a little bit of a demo in the last few minutes. So I'm just going to exit the presentation. And maybe I'm going to switch the screen that I'm sharing. So I'm going to stop sharing for a second and start again and pick this screen. Okay. Can folks see sort of the SyncroSim software here? So very quickly, when I first load SyncroSim, I need to get the packages that I want to work with. And similar to R, we have a package server. And so I would go install, and I want to work with STSim. You only have to, I'm going to go and download the STSim package from the package server, much like you would do in R. I'm also going to get the STSM SF package, and I'll also grab this package that folks might be interested, which is the Landfire Veg Models package. And click OK. So I've got my packages now downloaded from the package server, and now I can go and do something like a file new library to create a brand new library. One of the nice things you'll notice is that packages also allow package developers to distribute data sets. So if I wanted to create a new library for the Landfire Veg Models, which is the package, by the way, that has all of the reference condition models that Corey talked about, I could grab this template. It's quite a large one because it has over 900 models with results. So I'm not going to do it right now, but it will actually go and download that model library for you, and you can look at it in STSim. Similarly, STSim comes with some example data sets that you can work with. And we have some tutorials on our website that take you through working with these example data sets. But just given in the interest of time, I'm just going to go and grab, open an existing library that I have already. And so this is one of the exercises from our course, and it's kind of set up to show both STSim in the user interface and in the R interface as well. And so here I have what we call a model scenario. And if I open it up, I can see all of the settings for the inputs for this scenario. And one of the things you'll be familiar with is the transition pathway. So this is that very simple example of a model that I showed earlier on. It's got the deciduous, mixed, and coniferous state classes. And if I double click on one of these state classes, I can open and see the transitions, both in terms of their outcomes, so succession from mixed to conifer happening at age 20, and fire happening from mixed to deciduous happening with a probability of 0.005. I can also set the initial conditions for my landscape, and there's two ways of doing that. I can set them non-spatially, so define my landscape size and define how much area is in the different strata and states over time, or I can load rasters, which is the case in this example, that define the starting ecological zone, the management zones, and the state classes and ages for my model. And again, the terminology that you see here for ecozone harvest block is not hard-coded, so this is very flexible, the way you want to sort of use the language around your model, and that can all be set here in the definitions. If I go for terminology, here I've decided that I'm working on a landscape tracking the area in acres, and these are the words that I want to use to describe my stratification of my landscape. So that's now the one thing I'm going to show. I can choose to run this scenario here in the user interface. It's quite easy. I can click the run button, but I also want to show how you would do that using the R interface. So here I am in R, and I've got my, I'm going to load the libraries that I need to use for this example. In particular, I'm going to load the rsyncrosim package, which is on CRAN, and you can get from CRAN. And now that I've loaded that, the first thing that I need to do is I need to set my working directory and make sure that I've got the right one for where my library is. And then I'm just going to load that library that I just showed you in the user interface. So that library is called my exercise 8 library. It's for our course. And so now I can find out some things about this library. So we've got both projects and scenarios, and the project is where you define your model building blocks. I can get some information about that project and the library that it's associated with. And I'm going to one of the things I can do is I can say, okay, what are the state classes in this model? So we have what we call data sheets. Those are the different inputs for the model. And so here I've listed my state classes in that model. I've got conifer, deciduous, and mixed. I can get list all of the scenarios in the library. So this library has it's got a single scenario, the one that I'm showing you here. That's the no harvest scenario. And I can set a particular scenario. I'm going to get the no harvest scenario. Again, I've got that scenario. I've got some information about that scenario here. And I can run that scenario. So now I'm going to run that scenario. That's this run command here in our SyncroSim. And the scenario is running. This takes a couple of minutes.
Leonardo, you're very brave to do this live. I feel like, although you could probably do it in your sleep.
Yeah, I find sometimes Zoom slows things down a little bit, but here we go. It's done. The scenario's done. And so now if I come back in here and I refresh, you can see that there's a little green triangle that says there's results for this scenario. I can add this scenario to my results. And I can see the results here in the graphical user interface. So changes in state classes over time. Actually, I'll just resize that. Right, so here we've got conifer increasing, deciduous increasing, mixed decreasing. And I can do something similar as well in R. Again, I can get the raw output. Just grabbing that data from the library. And then I can manipulate that output. So summarize it across, in this case, I've summarized it across time steps and iterations, and I can summarize it even further across time steps. And finally, let's just look at conifer, and I can create a plot here in R. Right, so here we've got that same plot, conifer going from about 170,000 acres to over 200,000 acres, which matches what we're seeing in the user interface here. So that gives you a little bit of a flavor for the kind of work that you can do either in the, some people just only ever work in the user interface. And then once you get a little bit more serious about, large modeling projects, you often work in both the user interface and the R scripting environment, but it's not required. So just a couple of slides to wrap up. This slide here, and I'll just put it on the, make sure it ends up on the right screen because I've changed screens here. So I just want to show that this is from our user conference a few years ago. There's quite a large community around state and transition simulation modeling using STSM, and we really value the contributions, both in terms of the work that people are doing with the tools and the feedback that they provide to help us improve the tools. So definitely, if you're interested in working with these tools, reach out to us. And yeah, so we've got, you can go to syncrosim.com to get the software or get updates. We've got 2 pages for documentation, both for SyncroSim and for STSM. We've got some online forums, and we've got some training materials. I think Randy and Priscilla are going to be talking a little bit more about training next week. So please, if you're interested in doing more work with the tools, definitely reach out. And I apologize that I went a little bit over time.
No worries, these things happen. And that slide that Leonardo was just showing, I will include those links in the correspondence email that will go out tomorrow. So don't feel like you have to rush to write those things down. We do, I feel like we should probably take a few minutes to address any questions that may have arisen while you were speaking. Thank you very much for that very brave demonstration. If folks do have questions, please unmute yourself. feel free to do that. And I'm going to launch a poll that I'll put up on the screen right now. And if you want to minimize it and take it in a few minutes, feel free. Surely someone has a question out there.
Looks like somebody's got a raised hand, maybe.
Oh, Jeff, go ahead.
Hi, Leonardo. Thanks for great introduction. I was wondering, it seemed like, if I understood it right, you have in some of the simulations, you had a habitat suitability measure, and that was used to, say, set the initial states. Can that habitat suitability be taken into account in the progression of the simulation, or is that something that only goes into the initial states?
It can. It's one of the more advanced features. So, but there is a feature in the software that allows you to call an external, pause the simulation and call an external program. So that would be this, this feature here, where I could say, have an R script that's going to process my landscape for habitat suitability. And so I could call R and point to my script here and tell it, how often I want it to be called. So before specific time steps or after time steps. And so you could say, okay, every time step stop, look at the habitat suitability, and then provide some feedback to the model as to what you want to do to the landscape based on that habitat suitability. And there's work, probably the best example of that is work being done by Louis Provencher and others at the Nature Conservancy of Nevada, where they're looking at sage grouse habitat and restoration efforts, and where they dynamically link their state and transition simulation model to a sage grouse habitat suitability model. And I think they talk a little bit about that. I'm pretty sure there is so if you go to the STSim, docs.stsim.net publications, there's all the publications we know of that use STSim. And this paper here, Landscape Conservation Forecasting for Data Poor Species at Risk, by Louis Provencher and others, I think talks about that approach.
Thanks, Leonardo. Anybody else?
Hi, Leonardo. Randy here. You hinted at this through your slides, but I thought it might be useful for people to get a little bit more information on what inputs are required to run SyncroSim in a very basic way, up to some more sophisticated examples.
Yeah, that's a good question. I mean, for the most basic example, you could say that you need your conceptual model, right? Which is your boxes and arrows. And you need some way of defining your starting conditions. They don't have to be a map, your starting conditions. They could just be the amount of area in each state, which is what the landfire BPS models do. And you need some way of assigning rates to your transitions. And so there's a whole number of ways that people do that. You can look at historical data. You can look at using process-based models like we did with FARSITE. But even, often even in the absence of information, you can work with different experts and try to get at what the rates are. Often what we recommend in those cases is to make sure that you include the uncertainty in the rates, or at least do sensitivity analysis when you have uncertainty to try to understand, what are the impacts of that uncertainty on your model projections. Does that answer your question, Randy?
Yeah, thanks.
All right, last call for any other questions.